Alright, so today I'm going to talk about recursion, which is a pretty cool topic in computer science, but definitely one that people can have trouble wrapping their heads around at first. But basically what it means is a function that refers to itself in its own definition. So a function that is actually calling itself inside itself. And you might think that sounds weird or would cause some sort of infinite loop. And you're right. You have to put in some sort of base case, some conditional, where if it's true, it stops calling itself. Because otherwise it will just keep going on forever and cause a stack overflow. And so we're just going to walk through a couple examples here. The first one I'm going to do is a classic starter for recursion, the Fibonacci sequence. So if you don't know, the Fibonacci sequence is made by adding the previous number in the sequence to the number before that. So essentially, each number can be found by the sum of the previous two numbers. And this is sort of definitionally recursive. But you might notice that there has to be some kind of starting point, right? You have to start with some two numbers that you can add to create that first instance of the sum of the previous two. So that brings us to our base case. And that'll look like if n equals 0 or n equals 1. An important thing to note with recursion is you should start by trying to think of what your base case is. Like, what condition would cause the recursion to no longer actually be recursing? Like, where's the stopping point? Or, in this case, you can think of it as the starting point. Like, what numbers are we going to start with to define the sequence? And technically, mathematically, the Fibonacci sequence is defined to start with two numbers. I think maybe 1, 1, but it might be 0, 1, whatever. It's not really important for our purposes. It's sort of an arbitrary beginning. So what we're going to do here is just return n in the case that n is 0 or 1. And what this function is meant to do is return the nth Fibonacci number. So then else, this is our recursive case, and this is where we're going to actually refer to the Fibonacci function that we're defining. And here we can just call, well, we'll be returning it, but we'll be returning Fibonacci n minus 1 plus Fibonacci n minus 2. So what this is saying is, if n is not 1 or 0, we'll just determine what n is by taking the previous n and the one before that and adding them. And so if you think about what the computer is actually doing when you get to this line, it's calling this function again with now a number that is smaller by 1 and a number that is smaller by 2. But when it hits this, it'll go back up here and go back into the function. And so this will it'll keep looping through itself until it gets to this case where it'll just return, 0 or 1. And actually, we can say something more like if n is less than 1, because we don't want to deal with negatives. And if you think about it, as it keeps calling these and getting to smaller and smaller n's, it'll stop when n equals 1. So the only time it would have hit 0 is if we passed in 0 from the start. So what we can do here to display the results of this is we can loop through some range. Let's look at the first 15 of them. We can print Fibonacci I. And let's set end equal to space so they're all printed on one line. We can print a new line after. And I should also fix this. We want this to be less than or equal to 1. Cool. So you might recognize that depending on what start you want to use, these are the Fibonacci sequence. So to make this a little clearer, let's actually walk through what's happening. And we'll take I equals 3, for example. So we can call Fibonacci on 3, where n equals 3. It'll say if n is less than or equal to 1, and it's not, n is 3. So we'll hit this else case. And when we get here, we're actually calling our own function on n minus 1, and since n is 3, that'll equal 2. So we'll go back up here, where n now equals 2, and again, we won't hit this case. We'll go to the else, and this time, we'll call this on 1, because 2 minus 1 is 1, and that will hit the base case. So that'll go back up here again, but now n is 1, and so it'll just return n. It'll return 1. So while n was 2, we went in here and called this on 1, and it evaluated to 1. And then we added that to calling it on n minus 2, and since n was 2, we're passing in 0, and that'll hit the space case and return 0. So, and this was still inside that first recursive call where we passed in 3 minus 1. So this is all when n is 2 now. This returned 1, this returned 0. So in that first original call where n was 3, we called this on 2, it went in here, and this evaluated to 1, and this evaluated to 0. And that was all on the left-hand side here. So in that outermost call, this ends up evaluating to 1 plus 0, which is 1. And then we're doing another recursive call here. So this is going back up with n minus 2, which is 1. So when n is 1, we're again hitting this case and just returning 1. So in the end, when we called it on 3, we called it on 2, and it did like another iteration where it went into the else case and called it even again on 2 minus 1 and 2 minus 0. And those added to 1, and that was returned when n was 2. And that was all on the left-hand side, on the first call when n was 3. And then we add that to this side, and this only goes in once and hits the base case, because n will equal 1 when we pass in n minus 2, and that'll just return 1. So, when n was 3 on that first call, this evaluates to 1, this evaluates to 1, and we get 2. And as we can see from our result, when I was 0, we got 0, when I was 1, 1, I was 2, 2, and when I was 3, we did indeed get 2. So I'll walk through another example of recursion in my next video, in which I'll cover bubble sort, and I'll go through implementing it both iteratively and recursively. But if you like this video and want to see more content like it, please hit the like and subscribe buttons. Thanks for watching, and enjoy your day.